Okay, good morning. This is it. We've made it. This is your last module and last lecture. And I really, really like the assignments that I have for this module. You do have a homework and a lab associated with this. You'll see, this is the last time you see Henry walk across the computer screen. And I've used these assignments for all of my classes that I teach climate in, so in my environmental science class as well. And I wanted to find a topic that really brought together all of the topics that we've talked about, all the modules that we've had, and they all encompass climate change, climate change kind of encompasses all of these modules. So we're going to bring it all together and talk climate. We're going to go back a little bit and discuss climate versus weather. We talked about this in the weather module or in the atmosphere module. What climate is, the greenhouse effect, radiative forcings, feedbacks, and anomalies. And maybe some of this is reiteration to you. Maybe you're familiar with greenhouse gases and the greenhouse effect, but I hope that you leave this module understanding just a little bit more than what you thought you knew. Some vocabulary for you to get through. So we're going to circle back to the atmosphere module and discuss climate versus weather. So in the atmosphere module, we really defined what weather was, right? And weather is that state of the atmosphere that is a particular, specific, and well-defined point in space and time, generally short-term, between minutes and days. Weather forecasts have little statistical value beyond about 5 to 10 days, which is why your poor weather forecaster is changing things up rapidly. Don't blame them. They're doing the best they can. It's nonlinear and chaotic, but still predictable behavior associated with the physical evolution of the initial conditions into the future conditions. So basically, weather is considered in a short period of time in a very small geographic location. And we can really only estimate weather events out maybe 2 weeks, and that's if. And if you are constantly checking your weather app like I am, you'll know that like this week I'm supposed to be out on a boat on Thursday. And so I've been checking the weather forecast, and like 3 days ago it was supposed to be dumping rain, and I looked this morning and it's supposed to be like sunny and 70. So, which is great. I wanted sunny and 70 while I'm out on a boat, but it's difficult to predict, although predictable. And especially with climate change changing so much, weather is getting harder and harder to predict. Versus climate is long term. So this is something that spans years to decades. It involves components of the Earth system other than just the atmosphere. And this is a defining characteristic of climate. Weird. We're going to come back to that here in a second. It is expected, repeatable, responds predictably to a forcing, which we'll define in this lecture. And it's generally predictable on long timescales, so decades to centuries. And it is large, regional and larger spatial scales. So we're going to go through what all of this means and talk about how climate differs from weather as we go. So climate is determined by a region's climate system. And a climate system, this is going to sound so familiar, has 5 components. We got the geosphere. This was module 2. We have the hydrosphere, atmosphere, biosphere, and cryosphere. So all of these proponents play into a region's climate. How? Well, we've been through all of these modules. So the climate is influenced by the atmosphere. It is the most variable part of the climate system. And it all comes down to the composition and the movement of the atmosphere that is surrounding the Earth. It can change radically, and it can be influenced by natural and human-made factors. Oops. The hydrosphere, so changes to the hydrosphere can include variations in temperature and salinity, and this does occur at a much slower rate than changes to the atmosphere. But we talked about in the hydrosphere that if the Gulf Stream starts to change, or if Greenland melts entirely and we no longer have that cold, dense water starting that conveyor belt system, it's going to alter the climate. And yes, this is a lot This will take a lot longer than like atmospheric changes, but it will still alter the climate. The cryosphere, this is a generally consistent part of the climate system. Ice sheets and glaciers, they do a couple things. So they reflect sunlight. Well, we're going to talk about that. There's thermal conductivity of ice and permafrost, and those profoundly influence temperature. And as mentioned in the hydrosphere, the cryosphere helps regulate the thermohaline circulation or conveyor belt, which has an enormous influence on marine ecosystems and biodiversity and climate. Um, so this is the Greenland ice sheet, right? And then the biosphere. This is topography and vegetation influencing climate by helping determine how the sun's energy is used on Earth. Um, so, ooh, I don't know if I do it in this. I don't remember if I did this for anthroposphere. But there is a really cool program that allows you to see how land use has changed over time as humans have altered land use. So turning forests into agricultural use, that has directly affected our climate. Um, because this has to do with evaporation, transpiration, it also has to do with photosynthesis, and the color of the vegetation is actually more important than you might think. I'll try to bring this back later this lecture at the appropriate PowerPoint slide. Oh, and then through photosynthesis, plants help regulate the flow of greenhouse gases in the atmosphere. If you are unaware, and hopefully you're not at this point because we've talked about it, but carbon dioxide is a major greenhouse gas. And as part of photosynthesis, plants take in carbon dioxide. So plants really help regulate the carbon dioxide uh, uptake in our atmosphere. They're a huge proponent of climate. But regardless of what's in the world, every region in the world has different climates, and it usually is based on latitude. So some parts of the world are hot and rainy nearly every day, others are cold and snow-covered most of the year, and this has a few reasons why. So here's the Earth. Here's our equator at 0 degrees latitude. We can go all the way up to 90 degrees latitude to our poles, either 90 degrees north or 90 degrees south. And our climates are generally distributed via latitudinal geographic location. Remember that Mount Vernon is about 48 degrees latitude. So we're about here-ish. 48 degrees north. So we're about here on the Earth. Now, the reason that each pole or each latitude might have a different climate is for a few reasons. One of the biggest reasons is distance to the sun, basically, and surface area to the sun. The equator gets hit with sun rays very consistently and at an equal. Do I have a slide? Hold on, hold on. I feel like I have a slide. I do. This is a bad slide of it, though. Basically, at the equator, the sun is reflecting directly down onto the equator. Once you get further up or further south, those sun rays can deflect a little bit easier, which is why it gets cooler at the poles. The sun just doesn't hit these polar regions as frequently or as directly as the equator, which is also why if you ever go to like Hawaii, and you're like, wear sunscreen, and everyone's like, okay, but you're at sea level. It's really not that big of a deal. Those sun rays are way more direct than they're here in the Pacific Northwest. So I got sunburnt, like roasted when I was in Hawaii, even with sunscreen, just because you're getting that direct sunlight much more clearly. So with that being said, this equator tends to be a warmer climate system. So this is our tropical climate system. And this is a hot and humid zone. Also, because it's so hot, there's a lot of evaporation, which we talked about in the hydrosphere module. The average temperatures are greater than 64 degrees Fahrenheit year-round, and there's usually more than 59 inches of precip each year. That's a lot. That's a lot of precipitation. As we move upwards into, oh my God, there's my pointer, sorry, into the yellowy color here around 20 degrees latitude, we get dry. So these zones are dry because moisture is rapidly evaporating from the air and there is little precipitation. Also keep in mind, if you go back to the atmosphere module, these are where we have low pressure systems at the equator, and then we get high pressure systems and then low pressure systems, which affects weather. But those pressure systems are ultimately defined by the climate system. My cats are arguing. All right, let's move up in latitude to about 40 degrees. This is a temperate climate. In this zone, there are typically warm and humid summers with thunderstorms and mild winters. Let's move up even further to this purpley color. This is continental climate. These regions have warm to cool summers and very cold winters. In the winter, the zone can experience snowstorms, strong winds, and very cold temps, sometimes falling between or falling below negative 22 degrees Fahrenheit. Now, I'm going to show you this on this part of the map. So if we're at 48, you might be like, well, where are we? And what I like about this visual here in particular and why I chose it is because it's not so like blunt. Okay, well, here's where tropical meets dry. There's a gradation, right? And we are sort of in the midst of this gradation between, I would say, temperate and continental climate. And then polar is this blue color, and polar is going to be very cold. Even in summer, the temperatures have never go higher than 50 degrees Celsius. They don't get warm. And because of that, there's not a lot of evaporation, and thus not a lot of precipitation. So Antarctica is technically a desert. All right. So we're going to keep with this model here on the left. For your assignment this week, you're going to look at the Köppen climate zones. And this is sort of a zoom in on the United States. There are a couple really good websites that I've had former classes look at before that really define localized Köppen climate zones. And they will vary based on topography as well. So not only are we latitudinally climate defined, sorry, I'm trying to think of words as I say this, but it's also relatively dependent on topography. And our area here hosts the Cascade Mountains, right? So the colors are the same. And here in Skagit, it might be hard to see, but we're a little bit drier in the Skagit, and that's for a couple reasons. That's because we're right next to the islands, and Vancouver Island, which is here, which is not shown here, which sort of act as a rain shadow. So we don't get as much precipitation as the direct western flanks of the Cascades or as the Olympic Range over here. That's all this is saying. It all has to do with levels of precipitation. But I wouldn't necessarily say that we're dry. Like we're certainly not a desert here in the Skagit. But this Köppen map is saying, well, we're drier than we would be in the Olympics or along the western flanks of the Cascades because those are those rain shadows. And we are sort of in a weird little bubble that sometimes that rain misses. Obviously you've already seen the slide because I skimmed through it really quickly, but I love showing these slides for my climate science classes because if you're a Star Wars fan, which if you're not, you should be, but I'll try not to judge. The new ones suck, to be fair. Sorry, maybe that's an unpopular opinion, but I can't watch. I watched them once, whatever. But obviously I love the originals. And George Lucas, the creator of Star Wars, I don't know why he did this. It's not like he was scientifically sound in his Star Wars creations. But what I love about this is he literally created planets that were climate based, and the whole planet is a singular climate. So this first one here, this is Hoth. This is from the Empire Strikes Back at the beginning of the movie. And uh, Luke and Leia and Han Solo are all on this ice planet. So this is a very polar climate, Hoth. This is Tatooine. So Tatooine is where Luke grew up, and Tatooine is a desert planet. So it's a very dry planet. I have so many questions about this. Like, who would civilize a desert planet? I say that there's also the sci-fi movie Dune, where it's all about living on a desert planet, but they have colonized it for the spice that's their economic That's their moneymaker, and it helps with space travel and stuff. And then finally, this is Dagobah. And Dagobah is where Luke Skywalker goes to train as a Jedi in Empire Strikes Back and Return of the Jedi. No, I think he's mostly there in Empire Strikes Back. And this is where he meets Yoda. And this is a tropical planet. It's all rainforesty and swampy, and but I love pointing this out that George Lucas is a climate fiend too, I guess. So throughout this term, we've been talking about chemicals and compounds and all of these different proponents that make out greenhouse gases. And maybe that's a term that you've heard before. And maybe you even sort of understand what a greenhouse gas is. But I'm going to dive a little bit into it. And I'm going to preface this by saying we do get a little chemical here. So if you are not familiar with chemistry, that's okay. I'll try to break it down as much as possible. I'm not about to quiz you. Well, you will be quizzed a little bit, but I'm not about to test you on the chemical functions of carbon dioxide. I think it's really important to understand how this works and why the greenhouse effect is so potent. So the greenhouse effect um, is predominant with Earth because Earth has an atmosphere, right? So all of the other planets in our solar systems don't have an atmosphere. But this atmosphere works as an insulator and it has matter, right? We have discussed this in the past that our atmosphere has mass and matter because there are different compounds in it. So what happens is when that solar radiation goes through our atmosphere, and remember from the atmosphere module, we know it just goes straight through. There's nothing to absorb it. There's nothing to absorb or take in this atmosphere. There's nothing to absorb the solar radiation in the atmosphere. It goes straight through the atmosphere into Earth's surface. Whew, I don't know why that took a second to get out. So this radiation makes it to Earth's surface. And now Earth's surface is what is absorbing this solar radiation, right? And that Earth's surface then re-emits solar radiation as infrared radiation. And that comes back out of Earth's surface. Sometimes this solar radiation is reflected off of the atmosphere, like it might bounce off some of the matter that's in the atmosphere. Sometimes it goes through, and sometimes the radiation is reflected off of Earth and then bounced back out into the atmosphere. But once that solar radiation has been absorbed into Earth's surface, Earth re-emits it in infrared radiation. And a lot of times it just goes back out into space. Sometimes it's refracted, or we say refracted when it like bends at a certain spot because of difference of density or difference of composition. But what we're finding is happening more prominently is because of the matter in Earth's atmosphere, a lot of this heat is actually being reflected back into Earth's atmosphere. And this consistency here is actually heating up Earth's atmosphere. So when I say it is being reflected back, there are compounds within Earth's atmosphere that are assisting in the reflecting of the infrared radiation back into the atmosphere that's continuing to heat it up. Basically, let me go back. Basically, more and more of these compounds are blanketing Earth's atmosphere like an insulator. And so it's keeping that heat in Earth's atmosphere. And these are some of the greenhouse gases. Now, the most common greenhouse gas, or the most abundant greenhouse gas, tends to be a surprise to a lot of people. It's actually water vapor. So water vapor comes in the form of clouds, right? And clouds work as insulators. Sometimes it's just invisible gas in Earth's atmosphere. Water vapor, the chemical formula is H2O. This is water vapor down here in the bottom right-hand corner. And water has a unique property. And this property is super important for water. It's actually what helps a lot of organisms survive and thrive with water. But one of the properties of water is that it's actually what we call bent molecule. So it looks more like a V, then it's not straight across, it's bent. And what happens is this bent shape, let me do it like this. Here's my bent shape. Ugh, This is weird. It causes the heat to come up and basically bounce off these molecules and come back down. If it were straight, it might not do that necessarily, or it might be able to sit in the atmosphere like this and the heat could just slide right through. But because it's bent, it sort of works as like a cocooner. That's a terrible word to use. I don't know why I used cocooner. I don't know. It works as a V-shaped thing that will help things bounce back off of it. So the shape in which water is formed at makes it a greenhouse gas. Now, okay, I wasn't sure if I talked about it. It's not the most dangerous greenhouse gas because water vapor only sits in the atmosphere for days. Right? We evaporate water and then that water comes back down as precipitation. So it's not up in the atmosphere for very long. So that's what makes it a common but not necessarily dangerous greenhouse gas. Carbon dioxide is our second most abundant greenhouse gas, and this is really dangerous. But carbon dioxide is a linear molecule, so it is straight across. And you're like, okay, Emily, but didn't you say that if it sits like this, you can go up? Sure. But carbon dioxide is a non-polar molecule. I'm trying to find a way to break this down if you've never taken chemistry. So it's CO2. This little black dot in the middle here is carbon. And then these two red molecules are oxygen. And think about each element is like a battery with a charge. Carbon has a slight positive charge to it, like when you are putting batteries together, you want a positive and a negative charge next to each other, or a magnet, you want a positive and a negative, right? Opposites attract. Carbon has a slight positive charge, positive 4. Oxygen has a slight negative charge to it. It's negative 2. So because of this, you think, okay, well, this carbon wants to attract to the oxygen. Yes, it does. But you have two oxygens on either side. You have a positive charge and you have a negative charge. Sorry, the negative charge is the oxygen and the positive charge is the carbon. So what happens is you get this molecule that has a choice. It can go left and choose the oxygen on the left, or the carbon can choose the oxygen on the right. And it kind of wants to do both. So what it does is it goes really fast. It vibrates. So this carbon molecule is carbon dioxide molecule is vibrating super rapidly. And because of this movement of this molecule, if you're going like this, any energy it hits is going to bounce right off of this very vibrating, almost violent molecule. I shouldn't say violent, but you get the gist, and that it is moving so rapidly that any heat energy that strikes it is going to bounce right back down. So that's the problem with carbon dioxide. Methane is our third most abundant carbon greenhouse gas, and methane sort of looks like a cross. I don't put it down in the bottom. So this is similar to water in that it is a bent molecule, and if anything hits this methane, it's just going to bounce right back down. So basically, what I am trying to get at here is that the compounds, the most predominant greenhouse gas compounds that we have in our atmosphere, it's not necessarily that these compounds are toxic per se or poisonous. The way that they are shaped and the way that they are moved, that they move, is what is causing this heat to be retained in our lower atmosphere. And that's why these compounds are so problematic. The other problem, especially with carbon dioxide and methane, is that they have a longer residence time, which means I mentioned that water only stays in the atmosphere for like days, right? Carbon dioxide and methane will stay in the atmosphere for years. And because of that, the more we put into the atmosphere, it's going to take a lot longer for it to get out of the atmosphere. So it's just building up and building up and building up. Hi, sweet angel baby. I know. My son is doing something suspicious and I don't know what. It's fine. He hasn't died yet, so. Um, so this is a map, and this is what we call a budget for carbon. So when I say the word budget, think about um, like when you're balancing your finances, right? What you are bringing in with your salary, with your pay, should be about what you're putting out in bills, in food, in let's go out to eat for dinner because I have a little extra money this month. So the budget should be what comes in, should be what goes out, right? Our carbon budget, and carbon dioxide is part of that carbon budget, methane is part of that carbon budget, both greenhouse gases. Our carbon budget is not balanced right now. Um, I'm not going to go through all these numbers. You're welcome to look at this and sort of assess what's going on. But the blue are our reservoirs or our stores of natural carbon. And then the red arrows are the inputs and outputs of carbon. So let me find a good one. So burning of fossil fuels, this is our output of carbon into the atmosphere. Are you coming down? Come on. Um, Plants are inputting carbon into the soil. And basically, if you go through all of these, and this is not a great diagram in terms of if you add up all of the red, of course, it's not going to add up to the blue. Ooh, pardon me. Um, but there are budgets that show exactly how much are going in and exactly how much should be coming out. And what we are emitting into our atmosphere and into our ocean, into our reservoirs, basically, um, is far more than the storage is able to contain. So we're finding within these budgets, and there's a lot of models going into these budgets, and they get really confusing very quickly because, of course, you're like, well, burning fossil fuels, of course, but that can be broken down into cement production and oil and coal and all of the different fossil fuels and how much we're emitting every year. Same with plant respiration. That can be really hard to measure year by year. Um, so there are some really, really intricate models. This is actually a very simplified model of our carbon budget. And this carbon budget is not balanced. And so we are emitting more greenhouse gases into this atmosphere. And because of that, this carbon is just building up and building up and building up because its residence time is too long. We are emitting this material every year, more and more. Um, and it's not exiting our atmosphere early enough. We know this because we've been measuring it consistently since about 1956, 58, 1956 or 1958. I think this says 1958. This is one of my favorite graphs of all time. I should get it tattooed on me, honestly. So I won't. That's crazy. But it is a really cool graph. And it's a very famous graph in climate science and in atmospheric, geologic, and oceanographic sciences. So this guy, his name was John Keeling, and he decided he wanted to study the carbon dioxide concentration in the atmosphere. And he picked a spot where there was very little civilization and it was out in the middle of nowhere, out in the middle of the ocean, so he could get the most consistent, well-mixed balance of carbon dioxide. Because if you're measuring carbon dioxide next to like Beijing, you're going to get a huge value that's not necessarily accurate worldwide, right? So he decided, well, I'm going to go out to Mauna Loa in Hawaii, which is on the Big Island in Hawaii. And he set up shop, which is up high in the atmosphere, and it's out in the middle of the ocean. So that atmosphere there is going to have a well-mixed carbon dioxide concentration, which means it's going to get a good average carbon dioxide reading globally. And he started to measure carbon dioxide in the atmosphere. And he did it like by hand. And to be completely honest, I have no idea how he did this. He was a chemist. So he basically set up in his chemical laboratory the proponents to measure carbon dioxide. And he did this like 3 or 4 times a day. Bless his sweetheart, daily. I think he won the Nobel Prize for it in chemistry. He at least got a lot of recognition for it. He has since died, but I had the honor of meeting his son, Ralph Keeling, who also works for Scripps Oceanography. And the Keeling name is like, I'm trying to think of a good celebrity who's not problematic right now. Pedro Pascal. He's the Pedro Pascal of science. So And that's actually a really great analogy because so I got to meet Ralph Keeling. I almost did a PhD with Ralph Keeling, but Ralph did a lot of really gross calculus modeling. So he's also measuring the carbon dioxide uh, um, in the atmosphere, but he does a lot of ocean acidification work and how it's affecting the ocean, not necessarily just the atmosphere. And it was a lot of calculus and modeling. And he was like, "Oh, you haven't taken matrices yet? Well, that's a fun class." And I was like, "Absolutely not. You're delightful, but I will never work with you because I can't do calculus." Anyways, he is like Pedro Pascal because he was the sweetest human on the face of the planet and just so, so kind. And so I love teaching about this graph because not only is he entirely unproblematic, but the family is entirely unproblematic. And they came up with this beautiful graph. And basically what we're looking at, sorry for that anecdote. What we're looking at is from 1958 until 2020. Well, and it's we're still measuring this. Um, the concentration of CO2 is increasing. And it's not linear. So what a linear line would look like, okay, follow my mouse. If we were linear, it'd be like this. What we're seeing is a dramatic increase of CO2 concentration in our atmosphere. This is an exponential graph, meaning that what it's getting to is eventually this graph is going to start to go straight up, meaning that our carbon dioxide concentration is going to get hefty. And I also have talked to you about parts per million and what that means. Basically, if you have a little box, and in this box I have 1 million molecules, 410 of those molecules are going to be carbon dioxide, which doesn't seem like a lot. But we went from 310 to 410 in the course of, oh, math. See, this is why I couldn't work with Ralph. 2020 minus 1958, so 80 years ish. About 80 years, we have jumped up 100 parts per million of carbon dioxide, and we are just continuing to increase. The other thing to note is because it has such a long residence time, even if we were to stop all industry, all carbon dioxide emissions, we would still increase over the next 10 to 15 years because carbon dioxide stays in our atmosphere for that long. So when we're thinking about climate change and how to backtrack on climate change, we have to sort of take into account this window of like, well, we need an extra 20 years just to say this is how it's going to be for another 20 years until that carbon dioxide is out of the atmosphere, which is wild. And finally, the last thing I want to talk about with this graph is, so we're increasing in carbon dioxide as a general trend over 50 years, but we have these weird sinusoidal up and downs, up and downs, up and downs, up and downs. And you're like, where the heck is this coming from? Why do we have weird up and downs? So here's 2019, we go up, we go back down, and it's 2020. We go up, we go back down. So they're annual. These weird little jumps are annual changes of carbon dioxide. And what's cool about this is photosynthesis and respiration. So when we have a jump in CO2, this is the fall, this is autumn. This is when plants are starting to die. And when plants die, they respire. And as they respire, they release carbon dioxide out into the atmosphere. When we have a short drop in carbon dioxide, this is spring. This is when things are starting to grow and they're starting to turn green and beautiful and we get flowers. This is the intake of carbon dioxide into these plants, meaning that carbon dioxide is being depleted from our atmosphere. So these are the annual fluctuations of respiration, photosynthesis, respiration, photosynthesis. But in general, our trend in carbon dioxide is trending upward. Um, we've also been talking about forcings and what we call radiative forcings as part of climate. So greenhouse gases are an imperative part of the climate budget and sort of the carbon budget, right? But you also have to take into account what we call radiative forcing as part of this climate system. So these are different compounds. I liked this graph because it shows the different greenhouse gases as radiative forcings, but let's define what this means. So what happens when the amount of energy that enters the Earth's atmosphere is different from the amount that leaves it? So the amount of solar radiation that is coming into Earth's surface right now should be the same amount that's leaving. That is an equal budget. That's the budget that we want to see, right? Same as coming in is going out. But like I mentioned, that's not what's happening, right? We're getting a lot of solar radiation in, and a lot of um, this heat energy is staying behind. So the heat that we're losing is less than the heat that we're getting in, and that's warming our planet. Um, this graph is showing how each one of these proponents is driving that uh, imbalance of the forcing. So carbon dioxide is a huge radiative forcing that's causing the planet to warm up. So this is a change in energy balance in Earth's atmosphere, in that the input is more than our output right now. Incoming power should equal outgoing power, but it doesn't. And these are the reasons why. This is methane, CH4, so another huge radiative forcing a hole. This is one of the reasons. Halocarbons, this is nitrite. Is it nitrite? It's not nitrite. Nitrous oxide. This is nitrous oxide. Um, it is a greenhouse gas. It's a small greenhouse gas. This is carbon monoxide. I don't know what this is actually. Um, this looks like it's a variable of nitrate. Oh, nitrate, yeah. Aerosols, precursors. And what you'll note is here, this line here denotes that anything to the right of it is a positive radiative forcing, which doesn't mean that's a good thing. It means that, let me move my face. I think that's just, yeah, in drivers, that's all it says. It's that it is impacting the radiative forcings, but some of these proponents are acting as negative radiative forcings, meaning that they're actually helping take some of the greenhouse gases out of the atmosphere, or that they're helping with the temperature. They might help cool the system. And I know that that sounds really confusing. So this is a forcing. We're going to talk about feedbacks here in a second, but the three predominant forcings of climate are the sun acting as that heat input, greenhouse gases sort of keeping the heat inside the sun or inside Earth's atmosphere, and then clouds. Clouds are another major proponent, a major radiative forcing in climate. Um, and what's interesting about clouds is they can do one of two things. They can either keep all of the heat inside, right? Clouds act as an insulator. And remember, water vapor is the highest or is the most abundant greenhouse gas. But clouds can also do another thing, and we're going to talk about that with feedbacks. So a feedback is another really integral part of a climate system. It's a process that can either amplify or reduce the effects of these climate forcings, which is predominantly the sun's budget. So can these feedbacks okay, I guess I do like this depiction here. So can this feedback with the sun's energy, this feedback is going to create a change regarding how it interacts with the sun's energy. And that change will either speed up warming or it will slow down warming. So what does this mean? Let me give you some examples. My favorite, oh, JK, that was anticlimactic. We got to get through this one first. Although I like this slide, I'm not going to go through it. I lied. I like this slide because it really breaks down a forcing and then the feedbacks, which help trigger these forcings a little bit and help interact with these forcings. So I'm going to talk about three different feedbacks. Yes, I know, baby. They're all positive feedbacks, but water vapor can be a positive or a negative feedback. Okay. So the snow and ice albedo feedback. And what I'll say is that it is very similar to the cloud feedback. Come here, bub. I know. Lunch is in an hour, and she's not having it. She's like, no, feed me right now. So the ice albedo effect. This was you did something similar. You used Google Earth Pro, but this is from NOAA. And this was the Arctic ice sheet that has been changing around the edges, right? It's been getting smaller and smaller and smaller. Ice is bright white, right? If you've ever been out on a snowfield in a sunny day, you're like, oh my God, it's so bright. My poor little eyeballs can't handle this. Ice does something really interesting where it reflects sunlight back out into the atmosphere. This is called albedo. This is the albedo effect, in that the larger ice sheet you have, the more sun can actually be reflected out into the atmosphere and out into back into uh, the space. It is a positive feedback, but the in terms of the reflection. But what we're finding with particularly the Arctic ice sheet. Now, this is different for the Greenland ice sheet, which is why this is not part of this discussion, and the Antarctic ice sheet, because both the Greenland and the Antarctic ice sheet are over land. But this Arctic ice sheet is over the ocean. When you look around at the surrounding colors of the ocean versus the ocean is very dark, and dark colors will absorb more heat. This lighter color is going to reflect it, but because the surrounding ocean is taking in more solar radiation, it's warming this ocean enough to start melting this ice sheet back. And as this ice sheet begins to melt, it gets smaller, making the reflective surface smaller. So, what we have is the ocean is absorbing more more sunlight because it's getting larger by area around this ice sheet. So it's absorbing more sun, absorbing more solar radiation, meaning that it's going to melt that snow and ice, meaning that there's going to be less reflectivity, less reflectance from the ice. And because there's less reflectance, we have more open ocean that will then continue to warm faster. And then that's going to melt more snow and ice. And then you're going to have even less reflectivity. And then that's going to continue to melt. So we have this loop of just because we're melting, we're going to bring in more solar radiation and then we're going to continue to melt. This is a positive feedback because it is just feeding on itself. And when we hear positive feedback, you think, oh, well, that's a good thing, right? Because it's positive. This is not necessarily a good thing. A positive feedback is a driver for warmer temperatures. Um, what is this? This is, I imagine this is the water vapor. I don't know why I didn't talk about it. Yeah, okay, this has to be water vapor because this is what this is. So the other, one of the other feedbacks can kind of go one of two ways. So the water vapor, I'm trying to find a way to describe this, sorry. Because in the past, I think it can be a little bit confusing. Um, so with water vapor, it can do one of two things. What happens is we get warmer temperatures at Earth's surface, and that water at the surface, especially at the ocean, will evaporate. More water vapor is going to be a strong greenhouse gas. This is going to create more insulation. It's going to create more clouds, more precipitation, which is going to increase the temperature of Earth's surface. We're going to see more water vapor as per that. And then we're going to see more greenhouse gases, more absorption of upward surface. And it's another positive feedback loop where we see because water vapor is a greenhouse gas, it's going to continue to warm the Earth's surface, and then we're going to see more evaporation. Positive feedback, right? Again, not necessarily a positive thing because it is feeding into the warming of Earth's climate. However, what we're also seeing is if we get enough water vapor, and this is why climate science is so convoluted. We're going to warm the temperatures of Earth's surface. we are going to get more water vapor. But so sometimes water vapor, if it gets up high enough into Earth's stratosphere and troposphere, it can work as a greenhouse gas. But it can also help cool a system. So some evaporation from the surface um, is going to help cool a system because it's water. This is called lapse rate feedback, and it leads to decreased damped surface warming. So I know this is confusing, and it was really hard for me to find a negative feedback that worked with climate. But basically, water vapor in the atmosphere can do one of two things. It can warm it, or because it's condensation, it can actually help cool some of the surface level um, uh, regions. And sorry, I just had a metaphor pop in my head, so this is why I'm struggling with words. Think about if you've ever walked through fog before, it's cool, it's cold. Um, it has the ability to cool surface regions, which help cool the surface of Earth. So this is a negative feedback. So even though we're starting with warmer temperatures, this helps dampen climate effects. But if you get that water vapor up high enough, it will behave like a greenhouse gas and it will warm the atmosphere. So I'm sorry if that was confusing, but just know that water vapor can act as a climate amplifier or a climate dampener, depending on where it's at, located in the atmosphere, and where it's at latitudinally as well. Finally, the cloud albedo effect is basically the exact same as the ice albedo effect. But this was what I wanted to get at with clouds, is that it acts as a radiative forcing on its own in its own way. It is a greenhouse gas, but it is its own forcing because it can do one of two things. I know, climate is crazy. So we have Earth's surface re-emitting this infrared radiation, which is then warming the atmosphere at Earth's surface, right? However, similar to the ice albedo effect, if we have enough cloud coverage, a lot of the solar radiation coming from sun will get reflected off of this white surface. Now, okay, I've told a few people this. If you want, well, maybe this is the wrong political time to get into this science, but um, science and climate science, one of the things that a lot of people really, really want scientists for is what we call cloud physics. It is one of those complicated topics because clouds are so unpredictable in so many ways. And the ways that they form and the ways that they move, it's entirely dependent on precipitation, on atmospheric conditions, on wind and direction and humidity, water saturation level. Like there's so many proponents that go into how clouds are being made, but they're so important for the climate because if we can understand how clouds form, we can understand how they're going to alter our internal climate system as they work as an insulator. But also, we can really decipher, okay, well, how much reflectivity are we going to create with these clouds? And what balance do we need in which we want enough clouds to reflect the sunlight, but too much clouds and we're keeping this heat inside Earth's atmosphere? You know, it's this weird balance of do we want enough clouds? How long do we want these clouds for? Do we want clouds in the middle of the day to help reflect the sun, and then we want them to go away at night so all of the heat just goes out into the, you know, it's so complicated and so wild, but it's so fascinating too. So if you want to get your PhD in climate science, look into cloud physics because this is where all of the money is at right now, at least in terms of funding. People really want to fund research into better understanding clouds because it's so complicated. You'll need calculus for it, sorry. But cloud albedo is another positive feedback. We're seeing warmer temperatures, we're seeing more water vapor and more clouds. And because we're seeing these clouds absorb and re-emit long-wave radiation, we're seeing more warmer temperatures. But again, it can also work as a negative feedback in a reflectivity scenario. We're warming the Earth's surface, it's creating more precipitation, thus creating more evaporation, thus creating more clouds. And those clouds are ejecting Earth's or rejecting the solar radiation. So Feedbacks. If you get anything out of this spiel, feedbacks are just a way to either amplify those climatic scenarios and to help warm the atmosphere, or they help dampen the climatic effects and basically dampen um, or lessen Earth's warming capabilities. Finally, we're going to talk anomalies, and I've also brought up anomalies a few times in the class. El Nino and La Nina are very famous examples of anomalies, of weather anomalies. But the best way to define an anomaly is something that deviates from what is normal, average, or expected. So we collect data all the time, and this data has usually a trend, but sometimes we get a weird year where the trends are off. So this is a temperature anomaly in atmospheric carbon dioxide emission scale because carbon dioxide is directly correlated to temperature, we have found. So we have this scale from 1960 to 2020. This is basically the Keeling curve, just a little bit more anomalic. So we have this trend rising from 1958 to 2020, 2026, where we see not a linear scale, but we're starting to see an exponential trend in this carbon dioxide. So to the right is our carbon dioxide. Remember, we went from 310 to 410 in the matter of 50 years. Conversely, on this side is the temperature anomaly. So in Celsius, this is the change of our average climate globally. And we see a rise in that degrees Celsius from 1958 to 2020. We see it from, this started -2 degrees from the average, and we have gone up about 1 degree Celsius in the last 50 years, on average, globally. So each one of these lines depicts the temperature and the carbon dioxide influx every year. So it's an annual depiction. This is the trend as we go. Basically, we're seeing some years have different anomalies than others. So this was, I don't know, 2018 maybe. We had a weird hot year where on average we were 0.95 degrees Celsius hotter than previous years. In the 2000s, we had some anomalous cooler years. Anything that falls along this line, so this guy here, 1989, oh, my birth year, is about average. This is our expected data. Here's another really close expected data set. 20, I don't know, 19, maybe this is 2018. I don't know, whatever this year is. This is another expected result. This one's because they're so close to this trend. So as soon as we see this high peak here or this high peak here, even some of these shorter ones are still anomalous in that they don't match our average and expected trend. And we're seeing more and more anomalies. We're seeing cooler years and we're seeing hotter years and then cooler years and then significantly hotter years. So it's not like, yes, we're warming the planet, but the warming of the planet is really affecting how storms and how a lot of these anomalous effects and situations are sort of coming into play. Okay, we're gonna stop. I know that was a lot. I have taken whole classes on climate change, like term-long classes, because the content is so convoluted and in-depth. You need classes. I mean, you can get a whole degree in climate change. So I tried to break it down as best I could into why the planet is warming and what effects these are having in the radiative forcings. So please reach out if you have any questions. You have a couple really good activities. I will say the homework assignment I assign every single class for my climate change modules. And it is, I'm going to apologize in advance because he all of a sudden became really problematic this year. But I love, one of the reasons I got into climate change was this documentary that I watched in like, I don't know, it must have been 2020. And it was Leonardo DiCaprio and Nat Geo, National Geographic, did a documentary about climate change. And what I loved about it was that he went around the world and talked to everyday people, not just politicians, although we have politicians in this documentary as well. But he talked to like everyday people about how climate change was affecting agriculture in India and um, some of the orangutan populations in Indonesia. And it was just really eye-opening at the time. And that was one of the reasons that I was like, I had no idea that some of these things were happening globally that were really affecting other communities other than just the US. We live a very privileged sort of isolated lifestyle in a lot of ways. And so to see how climate change is affecting the globe was really fascinating to me. So I have you watch this documentary, and Leo DiCaprio, bless his sweetheart, his very problematic heart, is now running rampant with billionaires and dating women who are significantly younger than him. So think of Leo what you will. I do not care. I have my opinions as well, but I really, really do appreciate this documentary that he put out because it is eye-opening. So that's your homework. You'll do a little reflection. And then I found a really great database that you'll assess some climate information. And hopefully, I choose this one too because it's a little bit, um, it goes hand in hand with the weather assignment that you kind of did in the atmosphere module. So you'll get to see how weather is different on in data from climate. So if you have any questions, please reach out. It is your last module, so yay, you did it. And final exam will probably be up soon.